Welcome to the Explainer. If you've ever marveled at the absolute seamless chaos of a massive multiplayer battle, or wondered why a virtual car crash feels so incredibly visceral, well, you are in exactly the right place. Today, we're going to demystify video game physics. We're going to explore how developers engineer this amazing illusion of reality. And spoiler alert, it's often by exploiting the limits of modern computer hardware and, surprisingly, the blind spots in our very own minds. Okay, let's dive right into this. Imagine you're in the middle of a fast-paced multiplayer game, right? You jump off a moving platform, you're trying to grab a ledge. To make that game feel buttery smooth on your screen, your local client is actually rendering the world about 100 milliseconds in the past. It does this to seamlessly interpolate the movements of all the other players. But when your jump command finally reaches the server, it has a major job to do. It has to validate it. The server literally has to ask itself, wait, when this player pressed jump, were they actually near that ledge 100 milliseconds ago? Which brings us to Section 1, the multiplayer time machine rewinding the digital clock. We tend to think of game servers as just, simple data hubs, but they actually act as literal time machines. Think about it. Your client is already rendering 100 milliseconds in the past. Now, add in your network ping, let's say a fairly standard 100 millisecond round trip, and the server doesn't even see your input until 200 milliseconds after the event actually happened. So, from the server's perspective, your client is practically living in the future. To validate if you actually made that critical jump, the server has to rewind its entire physics state to perfectly recreate the world exactly as it was a fraction of a second ago. It's wild. Let's move on to Section 2, kinematics versus true physics, the cost of unpredictability. So why is calculating that tiny little 200 millisecond window in reverse such a massive computational headache? Well, it all comes down to how games generate motion. Back in the early days, games relied almost entirely on kinematics, basically playing pre-recorded, canned animations. It gave developers absolute control, and honestly, it was very easy on the processor. But modern games? They demand true physics. And that means dynamically simulating physical laws on the fly using heavy numerical formulas. Sure, it allows for unprescribed, completely unique interactions, but it is incredibly unpredictable and extremely computationally expensive. I mean, every single collision generates unique, on-the-fly variables. And this brilliantly illustrates just how much pressure the system is under. At a macro level, the game engine is already a heavily burdened beast. It's constantly juggling cinematic content, the user interface, real-time rendering, networking, artificial intelligence, the whole shebang. The physics simulation is just in there, fiercely fighting for processing power and memory against all of these other massive, resource-hungry components. Honestly, it's a miracle it works at all. And that perfectly sets up Section 3, the processing bottleneck, why hardware struggles. To really understand the sheer load placed on modern processors here, we can look at an exhaustive UCLA dissertation by Thomas Ye on real-time physics workloads. He found that every single frame, so at least 30 times a second, the engine goes through a very specific loop. First up is collision detection, which uses geometry to figure out what bodies are actually touching. But then comes the real kicker, the forward dynamic step. This involves solving highly complex equations known as linear complementary problems to calculate constraint forces. In plain English, that's the heavy mass that stops objects from just phasing right through one another. And this step is absolutely one of the most expensive parts of the entire simulator. Now, what's really interesting about this side is how developers manage that chaos. They don't try to calculate the whole world all at once. Instead, they break it down into islands of interconnected objects. And to save compute time within those little islands, they rely on joints to remove degrees of freedom, which are really just the various ways an object can move or rotate in 3D space. For instance, a simple ball joint removes 3 degrees of freedom, while a fixed joint removes 6. By strictly defining these constraints up front, the engine simply has way less raw math to calculate, streamlining the simulation for that specific island. It's a really clever trick. But listen, even with those smart optimizations, the toll on the CPU is just staggering. Ye's research pointed out that unlike standard scientific computation, the physics load in games is highly distributed and sparse. It dynamically generates massive maximum stack sizes. We're talking up to 2.9 megabytes in testing. That means there is a sheer, continuous, absolute avalanche of temporary floating point data being calculated every single frame. It absolutely hammers the CPU's L1 cache. It demands incredibly fast, short-term memory access just to keep the game from freezing up on you. Now, if we benchmark these physics workloads across mobile, console, desktop, and server architectures, the bottleneck becomes blatantly obvious. Take a look at that bare minimum target of 30 frames per second, represented by the red dashed line right there. Even incredibly powerful desktop and server processors struggle massively during dense scenarios. Think multi-car pileups or massive sprawling battle scenes. The hardware just sweats. Which leads us to our final part, Section 4, the error tolerance trick, exploiting human perception. So here is the million-dollar question. If the hardware literally can't handle the math, how on earth are we playing these games today? Well, to save the day, developers shift their focus entirely away from hard computer science and lean heavily into human psychology. You see, the core philosophy of a game physics engine is completely different from a scientific simulator. A scientific simulator, that needs to be mathematically perfect. But a game engine deliberately trades mathematical accuracy for stability and speed. Instead of solving exact physics using a really heavy big matrix approach, they use a highly parallel quick-step algorithm. It iteratively solves smaller problems to give a good enough approximation. The engine just needs to not crash and to look visually acceptable to the player. So, the crucial point is this phenomenal finding from Ye's research regarding perceptual believability. To put it bluntly, human perception is actually quite flawed, and game developers know it. 2.7%. I really want you to remember this exact number. Researchers found that a character's virtual limb could literally stretch or shrink by up to 2.7% due to a physics simulation glitch or a mathematical shortcut, and the average human brain wouldn't even register that the physical proportions of the character just changed. No way, right? But it's true. And developers ruthlessly exploit these psychological blind spots. Now, sure, if a limb stretches by 20%, yeah, you're going to immediately notice that error. It looks comical. But that magical 2.7% threshold, that gives the engine massive breathing room to aggressively cut corners on the math. Furthermore, this tolerance for error strictly increases when there is high-speed ballistic motion on screen, or when there is high scene clutter, like a giant explosion in a massive multiplayer battle. The more chaotic the screen gets, the less your brain notices the bad math. And that perfectly aligns with the exact moment the CPU needs to take those shortcuts the most. It's a match made in heaven. Let's move to the next point and see how this builds up. The ultimate physics accelerator pushing our interactive entertainment forward isn't a faster CPU, it's not a new GPU architecture. The ultimate hardware hack is actually the human brain's natural perceptual error tolerance. We are quite literally completing the simulation inside our own heads by subconsciously smoothing over all the digital imperfections. So, I'll leave you with this. If the complex physics of our favorite digital worlds, the very stability of the ground we virtually walk on, relies entirely on the biological flaws and shortcuts in our own perception, are we processing the game, or is the game actually processing us? Think about that for a second. Thank you so much for joining me on this explainer, and I really hope this changes the way you look at every virtual world you step into.